All right, so our next talk is from Nathan West. So Nathan is one of the core contributors to Green Radio, and he's the lead developer of Volk, which is what he's going to be talking about. So Volk is the part of Green Radio that makes everything run as fast as you want it to. And it's a really important part of the radio now, and it's a principal driver in terms of our software innovation project. So hand it over to Nathan.
So I work for the Network Research Lab. I started there full time in June. So I'm a student at OSU. So if you have open source Volk questions, use my OK State email. Otherwise, else fine. So brief look at the Volk organization. We broke off Volk into its own repository in April, I believe, this year. So it's now tracked at github.com/radio/Volk. And if you have issues, pull requests, go through there. All the code is GPL v3, that's not likely to change. And you have websites, that is libvolk.org. And so if you're not familiar with Volk, basically it stands for Vector Optimized Library Kernels. There's three primary things that Volk tries to do. There is collaboration, compatibility, and speed, and those are the priorities. So we want everyone to contribute, and we want code to work as many places as we can make it, and the motivation is actually trying to get code to be fast. So Volk is a library of SIMD functions, or SIMD optimized routines. Basically, that's single instruction, multiple data. And it's also a dispatcher and API. And that's kind of the real value of it. Similar to how Green Radio has lots of signal processing blocks, but the scheduler is kind of the magic in it. So there's also a dispatcher, and then it's also a build system. So I'll talk more about that later and what I mean by that. That's what Volk is. It's also, I don't actually know foreign languages, but it's apparently also Wolf in Russian, and then equivalent to the English Volk word in German. You can have all the fun work that you want with that. So in this talk, we're going to talk about those three priorities. There's speed, compatibility, and collaboration. I'm going to do them in reverse order. What's the least priority for the priorities sort of. The goal of this talk is I want everyone to be fluent in Volk. There's a couple of terms that are sort of important to use when talking about this. And then I'm going to also do a sort of brief, not really a tutorial, but I want everyone to understand that you can approach Volk, you can add code, and you can make your code run faster. And Volk provides an easy way to approach that. All right, so here's the motivation. So this is the speed aspect. So this is a diagram I made sort of view an operation that's happening in Beyond, which is the SIMD architecture for ARM. So we have some memory going down vertically, and then registers that get loaded up, and then there's a fuse multiply add operation, and that's sort of happening a lot. So there's these interleaved loads. So there's these interleaved loads where you load up your complex data with one instruction that loads 8 floats registers, and there's another load that loads 4 real taps to registers, and then there's one instruction that does the multiply and add across 4 floats. Then at the end, you would clean up this and turn it into one float. This is sort of the motivation for Volk. We want to do these types of, we want to make sure that our CPU is doing these types of operations because they're faster than issuing a single instruction to a single, or to operate on one piece of data. So here's another sort of look at the motivation for doing this. This is some disassembled code for Neon. I snipped out the actual Neon code, so this is compiled with GCC, and it actually did the right thing for the most part. So it actually omitted Neon instructions, and they're more or less equivalent to what I would have written by hand. The problem is, if you look here, this is our R11 and R10 are registers that hold address for our data. And you can see that it's moving the pointer from R11 or from R8 to R11, and then loading data. And then it increments, does the pointer incrementer on R8, and then does this copy again. Like, that's kind of weird. So even when the compiler does the right thing with the Neon instructions, it's still emitting sort of weird code that is not actually as good as it could be. So this is like the simplest case you could possibly get to. So if the compiler doesn't do this right, then we can definitely do better, more complex things. And if you actually handwrite the dot products, it will be faster than this. So that's sort of the motivation for doing Volk. So there's this problem when you write this kind of code is how do you make it work inside your application? The historical solution is you have some compiler definition that says, oh, I'm working on this architecture, so compile this code. And Volk actually does that, but it just hides the mess behind the scenes for you, so that your application looks nice. So when you write it looks nice, at least it just makes calls to Volk instead of having if-defenses everywhere. There's another sort of solution to this. There's what I'll call meta compilers. 3 of them are Volk, Spiral, and PFI. They're great, and they're probably a lot of fun to work on if you're doing a PhD in compilers. But I don't actually, well, Spiral is kind of a special case, but I don't like writing Volk or PFI because they're just sort of unnatural. They're another abstraction, basically. So this brings us to, well, the second concern, I believe, is how we do that. So there's this famous quote from David Wheeler that all problems in computer science can just be solved by another layer of iteration. And there's the corollary, if anyone knows that, is except for the problem of too many layers of iteration. So Volk has 2 abstractions that I'm going to cover. There's the architecture and the machine abstraction. So if you look in the Volk source tree, there's a folder called gem, and then inside there's 2 XML files, arcs.xml and machines.xml. And that contains basically some XML that describes these abstractions. So the architecture abstraction describes essentially the architecture name, so it's just a friendly human readable name, and then compiler flags that you need to use to get your compiler to actually compile your code. And then any alignment restrictions. So one of the caveats with some of this SIMD code is that, well, in code in general, is that you actually want your register, your buffers to always be aligned on some boundary. So this provides a way to basically describe what the alignment should be. And then there's a check name, which you can give it, you can write a C function, and then give the name of that function to arcs.xml. And there's some code that will compile that function and then run it, and then you return results. And the result is basically yes or no. And it's, do I actually have this architecture? Like, can I run this code? So that's another piece of the build system. And all the checks are defined in Volk CPU.simple.c, which is the template. So then there's the, actually let me go back here for a second. This is actually sort of a misnomer. I want to take a tangent here. So we call it the architecture because that's sort of the CPU term for it. It's actually a little bit more generic than that. So I was talking with someone at work recently, and he said, Volk was missing a lot of functions that I needed. So instead, I wrote 500 functions to help me port MATLAB code to C. And I used like GSL and something else and something else. And The thing is, you can actually sort of abuse the architecture abstraction to say, like, here's a GSL architecture, compile all this stuff with GSL, and it'll link against GSL for you. So that's a possible way that you can sort of use tricks to not necessarily use architecture, but just use a different feature. So if you don't have GSL, then it just won't run the GSL coding rule. All right, so machine abstraction. Machines are a collection of architectures that we actually see together. So you'll never see Neon and SSE together. So there's no like Neon SSE machine. And you probably see, when you run your radio, you probably see some message that says like, using Volk machine, generic SSE, ADX, something like that. And that's basically describing the architectures that are in your machine. And so some examples are Neon, generic. Generic is just plain, ordinary C code that will hopefully compile with any compiler. And then Orc is sort of an optional one for all the, anytime Orc is available, it's always optional. So here's the sort of naming scheme for Volk kernels. So I actually just realized I didn't define kernel or protokernel. So a kernel is just an operation that you want to do. So a dot product, like a real dot product, is a kernel. So the kernel name here is 32FC magnitude 32F. And then this is the protokernel name that includes the Neon fancy suites. So kernels are always in kernels/Volk/whatever.h. There's also protokernels that you can write in just assembly.s files, and they're in kernels, Volk, ASM, ARC, where ARC is like Neon. So here's the brief overview of the naming scheme. There's the Volk namespace. And you can actually, there's a mod tool in Volk. It's in a later slide, but you can actually make your own version of Volk. Have your own namespace. Then there's the input signature. This one is really simple because there's only 32-bit complex float going in. You can have a 32x2, and the x2 would just say there are two of them. And then there's the kernel name, and then there's the output signature. Alignment, so this is an unaligned version, so you can't do any alignment with that. And then there's the protokernel tag. And I included this one in particular because I got a lot of questions, what is a fancy suite? And it's actually, it comes from this book, so it's another brief tangent. So before I started doing Volk things, I was looking at the mailing list, and Brian Catalino is sort of suggesting that, it started from a conversation on tunnel.py, so that's all good things do. And Brian Catalino is suggesting that we start these wiki pages that have tutorials on different file layers and how to do signal processing. And then Tom comes back and says, oh yeah, I suggest using this like IEEE Signal Processing Magazine column for any students that want to learn DSP and comm theory. This is a great resource to just get short tutorials on how to do some problem. So I looked at it and I thought, all right, I'll do that. And so this is since March 30th. In April, I bought this book, which is basically includes all of the articles from that column in a single book. So if any other students are interested in that kind of thing, also you can borrow this book Friday during the Hack Fest. Feel free to have fun with it. So anyway, the API here gives you, so if you notice, it's mostly similar. We drop the U and the protokernel tag, and so that just gives you a magnitude function that you can call from your code. And then your code doesn't have to worry about what architectures are available, what machines available, whether it's unaligned or aligned. Will actually, the dispatcher will check for you whether it's aligned or not. So that's sort of the API that the build system generates for you. So then there's the dispatcher and the profiler. So I just mentioned the dispatcher. Profiler is called Volk Profile. If you've never run it before, you probably should. Basically, if you're familiar with FFT wisdom or that kind of idea, it's the same thing where it runs all the implementations that are available for your machine and then records the fastest aligned and unaligned versions. And then we'll write that to a file. The file is in your home directory .volk/volkconfig. It's just a plain text file with the kernel name, the order. I think it's unaligned and aligned version. And if you're having problems with something, you can actually go in there and just change whatever kernel you want to run. There's also a trick that if you set there's an environment variable you can set to always run the generic version as well. So at runtime, the dispatcher will look in this file, and this happens in lib volk rank arcs.c. So this will look at that file that the Volk profile has generated, and then use the best one for your machine we've measured. And then the dispatcher handles all the messy details of what architecture is running online. So putting it all together, this is sort of what I'm calling the Zen of Volk. So we have these architectures, and we write these header files that have implementations for as many architectures as you want. And so you hopefully have some like DSP engineer that can do this. Like they love to make things run fast. And then the build system generates these machines for you. And then the user generates this shared library or static library, and the user has some like GR signals that calls into libvolk and does fast code. And then you can profile your code, and if you find something that needs to run faster, then you come back here and say, oh, I need neon for this function. And it can do this. Yeah, so there's automated QA, which is also sort of the high value of Volk, is automated QA. It reads the function signature that you generate, and then automatically generates random data. It gives you a buffer, generates random data, and then feeds that same data into all of the protokernels for your kernel. And then compares the results of all the buffers to the generic version. So if you've done something, if your implementation has done something wrong, then hopefully the generic version is still intact unless you've messed up that buffer too, in which case you're exposed. And then we'll give you results. Like this is just wrong. Here are the elements that are wrong, and you can sort of fix that. So there's this automated QA, which is really useful. If your kernel doesn't fit inside of what the QA can generate, there are Volk puppets. So the rotator puppet is sort of the most infamous one because it was running first for a while, and it took a really long time to run. So several of you may have complained about that. Made it run faster for less items, and then made it run not first. So, yeah, puppets are a nice QA feature because if you have anything that just doesn't fit normally. So I think Johannes was having problems with the board codes, and puppets basically mostly solved his problem. Puppets are useful. So now on collaboration. So it is a collection of optimized signal processing routines. So this is a screenshot from the libvolk.org website. This is a table that I keep track of. It's a little out of date right now, but basically for every kernel we have, I have this table where the columns are the architectures that we have. So it's the aligned and unaligned for all the versions. So it doesn't make sense in this view because it's kind of hard to fit the whole thing on the slide. But there are things like the generic architecture, unaligned, aligned, and SSE. The numbers are the number of implementations for a particular architecture. So I get asked a lot, why is this one 2? That's because, so the one that I see at the top, there's SSE, there's SSE2, SSE3, SSE 4.1, 4.2. So I just count all those as SSE because they're all so similar. And there's 3 implementations for SSE for that. So if you're having problems with your block and you come in, look at this and say, this block is using this, and there's a 0 on this architecture that I care about. So you can go in and try to write the core kernel for your architecture. So this is where I encourage you to write the whole code. So there's the mod tool. It's similar to the radio mod tool, where it will give you make a new module, and whatever you want it to be called. So this is actually how the ARM, the neon implementations added. I had a little ARM that we worked on. And it's nice because it gives you ownership of the code. You don't have to contribute it back to the FSF. I encourage you to do so because it's generally useful. But it allows you to basically do whatever you want with your code. And experiment with new architectures, add whatever kernels you want. So some parting thoughts, Volk is sort of a necessity. In an ideal world where our compilers were extraordinarily smart and they did everything we wanted them to do, Volk probably wouldn't exist. Because the compiler would do it for us. But it is sort of a necessity, and it's actually not that bad to write Volk code. So you can read back upstream, making code run faster. And I just want to plug the working group for Volk. It's tomorrow at 3:30 downstairs. There's a few things I'd like to talk about. And if you have any general feedback on how Volk can be improved, that would be a good place to bring it up. So that's all.
All right. So we have a few minutes for questions. If anybody in the audience has a question or anything. No? Okay, so Nathan, I know Volk comes with a few for client programs that users use, like the benchmarking programs and that sort of thing. Can you comment on how people should use those and what is the most useful way to interpret the results?
Yeah, so the program that comes with Volk is Volk Profile. And that will actually write to standard out or your console what the time for every architecture that can run is. And so you can look at that and sort of say, oh, I definitely want this one. But then there's also an extension to that that Tim wrote, I think, 2 years ago at the Hackfest the conference, called GR Benchmark. So if you go on Tim O'Shea's GitHub, it's I think github.com/OSH GR Benchmark. You run that script and then say yes to upload results. It'll upload results to a website called stats.uniradio.org. And there we keep track of all the CPUs that this is run on, and then display the results for all the kernels and CPUs. So you can see what the fastest CPU that someone has run Volk on and send results back to. So that's kind of a useful way to gauge what a particular processor might be capable of, because it gives you, from code that's actually running in your radio, it will give you basically a flop count for all these different operations. And you can try to predict what might actually run on a CPU in real time. That's one utility that we have to build.
How often does Volk Profile need to be run when you revise Volk? Should you run the user running each time?
That's a really good question. So the question was, how often should Volk Profile be run? In general, it should be run, I would say, when you update. So the product kernels themselves don't change a whole lot, and the kernels don't. Well, the product kernels change more often than kernels. And whenever there's a new kernel to run, or whenever there's a new kernel in Volk, there's actually an option in Volk Profile that's -- updates. That's it. And that will only run new kernels. So it'll only benchmark new kernels. And that saves you a lot of time. So you should always, after updating, you might as well run Volk Profile -- update. There's a chance it does nothing. Or it might run for like 10 seconds and then write to the
Any idea on a laptop what the effect of CPU throttling is? I notice I never get the same answer twice.
Yeah, so the question is, what is the effect of CPU throttling, especially on laptops? And this is also a big problem on embedded devices, especially if there's no heatsink or if there's no fan on an embedded device. The governors or throttles like to kick in a whole lot. And there's actually a big difference. If you let the governor do whatever it wants to, what will probably happen is the first protokernel to run will be artificially slow, and then the rest will be fast because it picks up that you're doing a lot of work. So there are tools. I think CPU free utils is a Linux utility that you can use to turn off governors, and I found that to be really useful, especially if you get consistent results.
Does Volk do anything with GPUs?
Volk. So the question is, does Volk do anything with GPUs? And the answer is no. For the type of operations that are in Volk currently, it doesn't make a lot of sense to go to GPU just to do that. I will plug the coprocessor working group. I think that's today.
Yes, today's working groups are coprocessor acceleration and GRC, yes.
Yeah, so the coprocessor working group will have lots of people that care about doing things on GPUs.
Any further questions? Yes.
Any other projects using Volk yet?
So the question is, are there any other projects using Volk? And the answer is not really that I'm aware of. I've heard from people that are working on things like RedHawk that, I said RedHawk, sorry. And I know people that work on RedHawk have asked me multiple questions. I don't know if they're writing their RedHawk components to use Volk or if they're just using the radio blocks in RedHawk. But not really any significant way.
Martin?
Yeah, so you asked about the license. Yeah, the license is CPLv3. It's not likely to change. If that's actually a problem for you, I'm moderately curious to hear about it. If I'm feeling happy, I might have sympathy for you. But I am curious to know if the license actually causes an issue for you. That's sort of useful feedback.
Yes, Dan?
Sorry to follow up on that. I was just wondering about things like, I assume projects like NumPy or like comparative special MATLAB when they're doing Pinterest, they kind of have their own type of thing behind that. In the case of NumPy, would it benefit from, benefit from having full?
I don't know the details of NumPy, but I want to say they use a lot of old Fortran code. You don't know if
Yeah, like
that's true.
Floss and Logpack are back into NumPy.
Yeah, so NumPy has a lot of, that's the only reason NumPy is worth using is because they have a lot of loss behind it. So they might benefit from using Volk. Probably worth reaching out to them. Yeah.
Any further questions? All right, how about another round of applause for Nathan?